Welcome to Cambridge Chemistry channel with Sarwatahmed. Be sure to like the video and subscribe it. Really helps the channel to grow. Today I will be solving Cambridge Chemistry International AS and A Level Paper 2 Feb March 2022. Let's start. Question number 1. Figure 1.1 shows how the first ionization energy vary across period 2. So you know that the ionization energy is going to increase across the period. A part, construct an equation to represent the first ionization energy of oxygen, include state symbols. This is oxygen. So first ionization energy, oxygen gas minus +1 gaseous sign plus 1 electron. So this is the first ionization energy of oxygen, because 1 mole of first ionization energy is the energy when 1 mole of electron is evolved from the 1 mole of gaseous atom to form 1 mole of gaseous ion. Question number B1, state and explain the general trend in first ionization energies across period 2. As the figure shows, the general trend across the period is about ionization energy is increased. So first mark ionization energy across period 2 is increased. So this is carrying 1 marks due to increasing nuclear charge, mean positive charge, proton charge in the nucleus. So no need to write down this, but the nuclear charge mean positive proton charge in the nucleus. So it is known as nuclear charge. Increasing due to increasing nuclear charge, decreasing atomic radius or atomic radii of the elements, and constant shielding effect. Constant shielding effect mean as there are same shells across the period, so that's why shielding effect remain the constant. So across the period ionization energy is increased due to increasing nuclear charge. When the protons are going to increase across the period, atomic size is going to decrease due to the pull of valence shell due to the more attraction between the nucleus and the valence shell electrons. So there is same shell according to the across the period, so that's why constant shielding effect. So these three factors responsible to increase the first ionization energy across the period, because when there is nuclear charge increase, number of electrons are increased, so there is more attraction between the nucleus and the valence shell electrons. Hence it is very difficult or high energy is required to remove the electrons from the valence shell. Explain why ionization energy A in figure 1.1 does not follow the general trend in first ionization energy. So oxygen ionization energy of oxygen is less than ionization energy of nitrogen, because as oxygen has 1s2, look at the electronic configuration, 1s2, 2s2, 2p4, while nitrogen is 1s2, 2s2, 2p3. So p electrons, p shell is half filled, so there is no electron pair repulsion in the 2p3. One electron, but in case of oxygen there is spin pair repulsion, so less energy is required to remove the electron from the oxygen due to the pair repulsion of electrons in 2p orbitals. So there is pair repulsion of electrons in 2p orbitals of oxygen so when there is pair repulsion, so less energy is required, less energy is required to remove the electrons, hence oxygen does not follow the general trend. So pair repulsion is very important in this question. So to mention the pair repulsion is very important. Pair repulsion of 2p orbitals, hence there is a pair repulsion, so that's why less energy is required to remove the electron. So oxygen does not follow the general trend in first ionization energy. Next question is element E is in period 3 of the periodic table. The first 8 ionization energy values of E are shown in the table 1.1. 577, 18, 20, 22, 740, 11,614. So these are the ionization energies of the first, second, third, fourth, fifth, sixth, seventh and eighth elements. So element E is in the period 3, element C is element E is in period 3 of the periodic table. The first 8 ionization energy of E is given. So look at the ionization energy and identify the big jump in between the two electrons, two ionization energy. So first is 577, second is 1820 and third is 2740, and fourth is 11,600, and fifth is 14,000. So these energy values are almost same, and there is a big jump between third and fourth electron. So it means the element E is present in 13 group. So the electronic configuration of, because element is in third period and in 13 group of the periodic table, 13 group or third group of the periodic table. Third group, group determine the number of valential electrons. So this is electronic configuration: 1s2, 2s2, 2p6, 3s2, and 3p1. So this is the valence shell electrons. Because there is a big jump between third and fourth, so it determines that the element E is present in 13 group of the periodic table, or third group of the periodic table, third period and third group of the periodic table. So the explanation is, as there is a big jump between third and fourth ionization energy, so this shows that there are 3 electrons in the valence shell, and E is present in 13 group. Next question is, some oxides of elements in period 3 are shown: sodium oxide, aluminum oxide, phosphorus oxide, phosphorus 3 oxide and phosphorus 5 oxide, sulfur dioxide and sulfur trioxide. Sodium react with oxygen to form sodium oxide. Sodium is the reducing agent in this. Yes, define reducing agent. Reducing agent is a chemical species. Reducing agent is a chemical species which help to reduce others. Others after losing of electron. Or oxidized itself. Write an equation for the reaction of sodium oxide with water. Na2O plus water, sodium hydroxide. Aluminium oxide, question number part B is, aluminium oxide is an amphoteric oxide. Amphoteric oxide which share acidic and basic properties found in bauxite. State what is meant by amphoteric oxide. It reacts with acid and bases, or it shares acidic and basic properties. Aluminium oxide is purified from bauxite in several steps. The first step involves heating aluminium oxide with an excess of sodium oxide. A colorless solution forms. Write an equation for this reaction. Al2O3 plus sodium hydroxide plus water to form NaAlOH4 plus water. Constituents balance the reaction. Sodium Al2O3, place 2 over here, 2 over here. Third part is aluminum oxide is used as a catalyst in the dehydration of alcohol. State the effect of using aluminum oxide as a catalyst in the dehydration of alcohols. Use the Boltzmann distribution in figure 2.1 to help explain your answer. Aluminum oxide is used dehydration of alcohol. So for example, we know that this is activation energy with catalyst, and this is without catalyst. This part has greater proportion of the molecules having more energy. So in this diagram, this is EA with activation energy with catalyst, and this is activation energy without catalyst. Without catalyst. So this portion occupy less proportion of the molecules, while this proportion occupy the more proportion, of which indicates that the aluminum oxide lowers the activation energy. So but this does not mean that if this line is higher, so it means that it has higher activation energy. So in this Boltzmann distribution curves, this line indicates, the bigger line indicates activation energy with catalyst, and smaller line indicates the activation energy without catalyst, because this is the portion, the graph is the proportion of the molecules with higher energy. So in the presence of catalyst, molecules have higher activation energy, higher energy, so that's why they react with the reactant molecules to speed up the rate of reaction. So that's why a greater proportion of molecules, a greater proportion of molecules have more energy and they collide more often. Or frequency of, you can write down, or frequency of effective collisions. In this question, this carrying by drawing the by labeling this graph is 1 mark, and greater proportion of description is carrying 2 other marks, that molecules have more energy, greater proportion of molecules have more energy, and more frequent collisions. 1 mark for this labeling and 2 marks, 1 for this and 1 for effective collisions in the presence of catalyst. So next question is P4O6 is a white solid that has a melting point of 24 degrees centigrade. Solid P4O6 react with water to form H3PO3. Deduce the type of structure and bonding shown by P4O6, phosphorus 3 oxide. Explain your answer. Structure and bonding. The structure is simple molecule. P4O6 is a simple molecule, simple covalent molecule. So it is covalent compound, so that's why, and simple covalent and simple molecular compound, so it has a low melting point. It has low melting point and reacts with water to form H3O4. It is non-metallic oxide or acidic oxide. And acidic oxide, this is the property of acidic oxide: when it dissolves, they are hydrolyzed when it dissolve in water to form acidic solution. So H3PO4 is an acid, so when it dissolves in water, it forms acid. Low melting point and dissolved structure is simple molecule and bonding is covalent. Covalent, simple molecule is the structure and covalent are bond. Dissolves in water or hydrolyzed. To form acid, as P4O6 is an acidic oxide. Determine the oxidation number of P in H3PO4. H3PO3, you know that talks about how to find out oxidation number. H3PO3 is equal to 0, P underlined oxygen plus 1 and minus 2. So 1 into 3 plus X plus 3 minus 2 is equal to 0, and 3 plus x minus 6 is equal to 0. So x minus 3 is equal to 0, x is equal to plus 3. So oxidation number of P in H3PO4 is plus 3. When phosphorus 3 oxide is heated, P4O6 is phosphorus 3 oxide. With oxygen it forms P4O10. P4O6 plus 2O2 to form P4O10. The enthalpy change of formation of delta HF of P4O10 is minus 3012 kilojoule. Calculate the enthalpy change of formation. Calculate the enthalpy change of formation of delta HF of P4O6. So this is according to Hess cycle. P4O6 plus oxygen to form P4O10. So these are elements plus 4P and O2, 2O2. And this is arrow is towards this. This is delta HF, and this is delta HR, that is minus 3012, and delta HF is equal to delta HF, because minus delta HF minus this is delta HF of P4O10 minus 3012, while and we have to find out this, and delta HR is equal to minus 1372. So this is the formation of, so by joining the tail of this head of this and tail of this, so this is delta HF P4O10 is equal to delta HF P4O6 plus delta HR minus 3012 is equal to x plus 1372. Which is equal to minus 1640. Write an equation for the reaction of P4O10 with water. To form acid, phosphoric acid, H3PO4. This is 4, to balance is 4H3, 4 3s are 12, and 4 fours are 16. Sulfur dioxide and sulfur trioxide are found in the atmosphere. Equation 1 is sulfur dioxide plus nitrogen dioxide to form sulfur trioxide and nitrogen monoxide. Construct an equation to show how nitrogen dioxide is regenerated in the catalytic oxidation of sulfur dioxide. Sulfur dioxide and sulfur trioxide. Sulfur dioxide and sulfur trioxide are found in atmosphere. The oxidation of sulfur di and sulfur trioxide in atmosphere is catalyzed by nitrogen dioxide. The first step of the catalytic oxidation is shown in equation 1. Construct an equation to show how nitrogen dioxide is regenerated in the catalytic oxidation of sulfur dioxide. So the reaction is NO plus half oxygen to form NO2. NO2 can also react with unburnt hydrocarbons to form photochemical smog. Photo mean light, sunlight or light. Photo mean light, the reaction which takes place in the presence of sunlight. So to form photochemical smog. State the product of this reaction that contributes to the photochemical smog. You know that in core exhaust nitrogen dioxide, carbon dioxide are released from the car exhaust, and you know that when these are the directly emitted from the car exhaust, but nitrogen can also react with unburnt. So when it reacts with unburnt hydrocarbon to form photochemical smog. When it reacts with unburnt hydrocarbon, this photochemical smog is produced when nitrogen dioxide is emitted from car exhaust, and it can react with unburnt hydrocarbon to form photochemical smog. State the product of this reaction that contribute to photochemical smog. You know, nitrogen dioxide when react with volatile organic compounds, unburnt volatile organic compound which is unburnt hydrocarbon so when it reacts with nitrogen dioxide in the presence of sunlight to form PAN. PAN is the product that contributes to photochemical smog, which is produced by reacting with nitrogen dioxide in the presence of sunlight, and PAN is abbreviation of P stands for peroxy, A stands for acetyl, and N stands for nitrate. peroxyacetyl. So the formula of this compound is CH3 CO3 NO2. The structural formula is C double bond O O N O 3. So this is pollutant which is formed by reacting with nitrogen dioxide, and this contributes to photochemical smog, which affect the eyes and lungs. Part 3 is figure 2.2 shows how the temperature of the atmosphere varies with the height from the ground. This is temperature height of 20 kilometer, temperature is low. Height of 50, temperature is high, temperature is low. At 150, temperature is high, and 90 kilometer temperature gain, it is very low, and at 110 it is high temperature. The equilibrium reaction of in equation 1. Equation 1 is, this is equation 1, SO2 plus NO2 to form SO3, and SO2 plus NO2, SO2 plus NO2 to form SO3 plus NO, and this is exothermic reaction because delta HR is negative. Exothermic reaction. The equilibrium reaction in equation 1 has delta HR is minus 168 kilojoule per. Suggest how the position of equilibrium differs at the height of 20 kilometer compared with height of 50 kilometer from the ground. Explain your answer. So because delta HR is 168, so forward reaction is exothermic. So if forward reaction is exothermic, this is reversible reaction, then backward reaction is endothermic. And look at the temperature, 20 kilometer temperature is low. So at 20, suggest how the position of equilibrium affect the height of 20 kilometer compared with height of 50 kilometer, as we have discussed earlier. 20 kilometer temperature is low or 50 kilometer temperature is high. At height of 20 kilometer, temperature is decreased. Equilibrium will shift backward. forward, because low temperature favors the exothermic reaction in case of overall exothermic. If overall exothermic reaction, so by decreasing temperature favors the exothermic side. Equilibrium shifts forward and more sulfur trioxide and nitrogen monoxide are formed. At 50 kilometer height, temperature is increased. Equilibrium will shift backward. As backward reaction is endothermic. And more sulfur dioxide and nitrogen, more sulfur dioxide and nitrogen monoxide are produced. Question number 3, the hydrogen halides HCl, HBr and HI are colorless gases at room temperature. Part A, the hydrogen halides can be formed by reacting the halogens with hydrogen. Describe and explain the relative reactivity of the halogens down the group when they react with hydrogen to form HCl and HBr and HI. So these are the halides of group 7. Halides of group 7. HCl, HF, HBr and HI, and we know that across the down the group reactivity of halogen is decreased due to increasing number of shells, and atomic radii. So there is more difficult to react hydrogen with iodine down the group. The answer is the reactivity of halogens are decreased downward or down the group due to increasing atomic radii of halogens so it become difficult to attract valence electrons of other atom. And this is trend across the period. Hydrogen react with chlorine to form HCl. So this is irreversible reaction. H2 plus Br2 to form 2HBr. This is slow reaction and H2 plus I2. This is reversible reaction. 2HI. So this is the reason. HCl is a product of several different reactions. Some of these are shown in figure 3.1. SiCl4 react with reaction 1, react with H2O to form HCl. NaCl react with concentrated sulfuric acid to form HCl. Write an equation for the reaction 1. SiCl4 then react with water to form silica plus HCl. So silic 4HCl. Now SiO2, we place 2 over here. Part 2 is in reaction 2, NaCl react with concentrated sulfuric acid to form HCl and NaHSO4. Then NaBr react with concentrated sulfuric acid. NaCl react with to form HCl, NaHSO4. When NaBr react with concentrated sulfuric acid, the products include bromine and sulfur dioxide. Identify the type of reaction that occurs in each case. In each case, by completing the table 3.1, explain the difference in these reactions. NaCl reacts with the concentrated sulfuric acid plus H2SO4 to form NaHSO4 plus HCl. While NaBr react with sulfuric acid to form NaHSO4 plus HBr, and HBr is further oxidized by sulfuric acid to form Br2 and SO2. So type of reaction is explain the difference in these reactions. Sodium chloride and concentrated sulfuric acid. Sodium chloride HCl is Cl negative is not oxidized by sulfuric acid because sulfuric acid is weaker oxidizing agent than Cl negative. So this reaction is cannot oxidize HCl. So this reaction sodium chloride and sulfuric acid is acid base reaction. Or displacement reaction, you can say displacement reaction. But in next reaction, NaBr plus H2SO4, NaHSO4, HBr is unstable, which is further oxidized by sulfuric acid. So in above case, sulfuric acid is chloride is stronger oxidizing agent than sulfuric acid, so cannot oxidize. But in this case, HBr is a weaker oxidizing agent than sulfuric acid, so HBr is further oxidized by sulfuric acid to form Br2 and sulfur dioxide. So second reaction is redox. Identify the types of reaction that occur in each case by completing the Explain the difference in these reactions. Chloride ion is stronger oxidizing agent oxidizing agent than sulfuric acid, hence cannot further oxidized by H2SO4, while in case of while Br negative is weaker oxidizing agent than sulfuric acid. So further oxidized to form sulfur dioxide and Br2. So in other words, you can say that bromide ion is a stronger reducing agent than chloride ion. So that's why bromide ion reduces sulfuric acid to form sulfur dioxide. When heated with Bunsen burner, HCl does not decompose, whereas Hi from H2 and I2. Explain the difference in the effect of heating on HCl and H. As we have discussed earlier that down the group reactivity is decreased due to increasing atomic radius or due to increasing the shielding effect. So explain the difference in the effect of heating on HCl. So Hi is unstable compound than HCl. So HCl is we can say that Hi is less thermally stable due to larger atomic size of or radius of the iodine, which causes an increase in bond length. So we know that longer the bond length, more the energy, less the energy is required to break the bonds. So increase in bond length, hence less energy is required. So that's why hydrogen iodide is thermally hydrogen iodide is less thermally stable due to larger atomic radius, less energy or less bond energy. The hydrogen halides dissolve in water to form strong Bronsted-Lowry acids. The concentration of strong acid can be determined by titration. State what is meant by strong Bronsted-Lowry acid. Proton donor is according to Bronsted-Lowry. Proton donor is an acid and proton acceptor is base. So what is meant by strong Bronsted acid? Bronsted Lowry acid is proton donor, which is completely strong, mean which is completely ionized. Ionized in aqueous solution. On figure 3.2, sketch the pH titration curves produced when 0.1 mole dm cube sodium hydroxide is added to 25 centimeter cube of 0.1 mole HBr to excess 0.1 mole, and second titration curve is 0.1 mole dm cube per dm cube ammonia is added to 25 centimeter cube of 0.1 mole dm cube HBr to excess. Okay, sodium hydroxide is added. So this is the titration curve, and we know sodium hydroxide when react with HBr is the strongest acid, sodium hydroxide is alkali, reacting 1:1, and volume is 25 centimeter cube of 0.1 HBr. So this is the strong acid. Starting curve draw like this. So this is and strong base. It's again 25 centimeter cube. Draw like this. And ammonia is a weak base. Starting from here. HBr is a strong acid. Ammonia is a base. Starting from the same point. HBr reacts with propene to form 2-bromoalkane, CH3, CH2, CH2Br, and CH3 tertiary haloalkane. Complete the diagram to show the mechanism of the reaction of HBr and propene to form the major organic product. Include charges, dipoles, lone pairs of electrons, and curly arrows as appropriate. Draw the structure of the intermediate. So this is carrying partial negative, partial positive, and then come close to this. This is arrow, and to form carrying positive charge CH3, sorry, H, this is H, Br negative. This is intermediate product. Excuse me. C. This is positive charge and Br negative. Explain why the two bromo alkanes are not produced in equal amount by this reaction. The secondary carbocation. This is secondary carbocation. This is secondary carbocation. So the secondary carbocation is more stable due to higher, due to more positive inductive effect. Electron the reaction of CH3CH2 CH2Br and sodium hydroxide is different depending on whether water or ethanol is used as a solvent. Complete table 3.2 to identify the organic and inorganic products of the reaction of CH3CH2 propane bromide and sodium hydroxide in each solvent. Inorganic product, organic product, sodium hydroxide. We know that when water is the product, the organic products would be, solvent is water. So when aqueous or water is used in aqueous medium, OH is formed, alcohol is formed. CH3 nucleophilic substitution, CH3 CH2 CH2OH, and the inorganic product would be, because sodium, so this is sodium bromide is formed, NaBr. While in case of ethanolic medium, elimination reaction takes place and CH3 CH double bond CH2 is the organic product and HBr is the inorganic product. The last question is, compound J and K are found in plant oils. Complete the table 4.1 to state what you would observe when J reacts with the reagent listed. 2,4-dinitrophenyl hydrazine. Observation with J. This is ketone group, and on the other hand this is aldehyde. So this is carbonyl group because ketone and aldehyde both are present, and in both cases ketone and aldehyde, the positive test of with 2,4-dinitrophenylhydrazine, that is orange precipitate. PPTs are produced, and tolerant reagent because due to the positive test with aldehyde, but no observation with ketone, but in this compound aldehyde is present, so that's why silver mirror formation. And with sodium metals, because OH group is present, so due to the OH sodium, when sodium react, so CONA is formed along with bubbles of hydrogen gas. J has two optical isomers. Draw the three-dimensional structure of the two optical isomers of J. So optical isomers which have four different groups are attached with carbon atom. So this is chiral carbon, this is chiral carbon. Carbon is surrounded by four different groups: C double bond O, H3C, CHO, CH3 and OH. So we know that the optical isomerism, in which two compounds, two isomers are superimposable mirror images of each other. So this is the structure OH, CHO, CH3, C double bond O, H3C. HO, OHC, H3C, and CH3. J has two optical. K is used to make the addition polymer Perspex. A synthesis of Perspex is shown in figure 4.2. This is K and reactant L to form reaction 1 CH3 COCH3. So this is COCH3. It means methanol reactant L is methanol, and reaction 2 Perspex is formed. So this is reaction 2 is polymerization because Perspex is polymer. And state the conditions required for L is the methanol. and conditions concentrated, because this is esterification, this is carboxylic acid, and now ester is formed, COCH3. So the condition is concentrated H2SO4. Draw one repeat unit. This is the Perspex. So one repeat unit, this is very simple question, very easy and simple. COCH3 CH3. This is one repeat unit. Use information from table 4.2 suggest how the infrared spectra of M and Perspex. M. This is M. M is double bond, while in polymer and Perspex there is no double bond. You explain your reasoning. So table different values are given, and you know that M C to C double bond 1500 to 1600 1680 values. So because this is present in M, so different how the infrared spectrum M and Perspex would differ. So we'll write down in M there will be an absorption at 1500 to 1680 due to carbon double bond in M, which is absent in Perspex. And in Perspex C double bond O is present, so their absorption is carboxyl absorption is this. Part 4, K can be made from propanol in the 3-step synthesis shown figure 4.3. So propanol step 1. In step 1 this is ketone group, and in step 1 OH group and C double bond cyanide group is formed. So step 1, reagents, complete the 4.3 to identify reagents used and type of reaction in each step. So over here this is seen, cyanide group is nucleophilic addition, reaction is nucleophilic addition, and the reagent are NaCN plus HCl and nucleophilic addition. In step 2, this is oxidized to form carboxylic acid, and OH remain the same. So water, aqueous acid, dilute acid, and reaction is hydrolyzed to form CN is cyanide group is hydrolyzed to form carboxylic acid. Hydrolysis. And in step 3, COOH, K is formed. OH is eliminated to form double bond over here. So OH is eliminated and double bond is present here. So this is elimination or dehydration. Water is removed. So this H and this H and this elimination or dehydration. So this is end of this paper. This is last question. Hope you will understand. If you have any question, please ask in comment box, and if you like this video, please subscribe and share this video with others.